everyone. It is June 25th, 2024, and this is the bi-weekly libhal meeting. All right, so we have quite a few items on the agenda. First, I'm going to talk about EastConts. I'm going to talk about preconditions and error service area. We're going to go over the SPI bit order policy. I never really defined this before, and now I'm going to define it. I'm going to talk about the refactors of the ARM interrupt API. I'm going to talk about renaming hardware map. I'm renaming it to resource list. We'll talk about that in a sec. Also, another renaming for libhal platform. I'm going to show you the ARM Cortex platform bring up guide, which should explain to you all the pieces you need to bring it up with Conan using libhal. And also gives you structures out some basic things that your particular implementation or your particular platform should support. And if it doesn't support something, then you just eliminate those parts. We'll go over the extended fundamentals doc. I added more library categories. And then finally, I think the biggest and most interesting thing will be the low power strategy. Okay. All right, so first off, we have EastConst. Oh, hold on, someone needs to mute. Can someone mute real quick? Or everyone who's on here, can they mute? Testing 1, 2, 3. Cool, all right. So I have a problem with memorizing westconst or const west, and EastConst is easier to explain to everyone. Basically, there's only one rule. Whatever's left of const is constant. That's it. So if you have a thing, a reference, and a pointer, if you put const in the middle, the link to the left, the integer itself is constant. If you have an int const ref, then that means that the integer is constant and it's a reference to a constant int. If you have an int const pointer, then the integer is const, the pointer is mutable, so you could reassign the pointer. If you put const in front of the asterisk, then the pointer is const, the integer itself is mutable. And which I don't know. Oh yeah, this I here is immutable, so yeah. And then finally we have int const pointer const, which just means that the integer is constant and the integer is constant and the pointer is constant. So this thing points to a constant integer. You cannot reassign the pointer, and you cannot update or change the value of the integer either. With const west, it's very widespread, but it can be a little confusing to figure out where to place things. Overall, I think this is pretty simple. Right now, because I made this change, I made it in libhal, and the CI is designed such that libhal's claim format is the claim format that is tested against. It does not use the claim format that's in the repo. Actually, the claim format in the repo is just a copy of whatever's on libhal. So the reason why I do this is such that we can broadcast out changes to claim format in the future. So you can know that someone's broken that if their lint breaks because we updated the libhal. It may seem like a bad thing, but I think having people's builds break gives more urgency to fixing them, especially in the future where that will be probably more of a concern, especially as we potentially have more users. So that's pretty much EastConts. Actually, are there any questions about this in particular? Cool. Next up, we have preconditions and error surface area. The first thing I want to say, and I have an issue tracking this to write more documentation on this to kind of explain it a little bit further. But basically, I hate APIs with preconditions. Full stop. If there's an API where I need to call other APIs before I can call the API that I want, I'd hate that. It's among the reasons why, I used to have a lot of code that had a .init function, like init functions and that kind of thing. I also hate those with a passion. The thing I don't like about precondition functions is two things. One, it adds more conditionals and it adds more state to an object. And there's already a lot of state that systems have to deal with. If there are arbitrary conditions added on top of that, there's more checks you have to do. More branches, don't like it. And it's also harder for the user to reason about because they have to kind of make sure that they did the prior sequence of steps appropriately before they can call your API. And I feel like this basically increases the error surface area. Or even, I forgot to put this down, it should also increase the bug surface area. So the error surface area is if you call this API before calling another one, it might throw or emit an error of some sort. That is increasing the error surface area. It also increases the bug surface area because it's a place where you could make a mistake. You didn't do this one precondition beforehand. You didn't get the system set up beforehand. Therefore, this thing acts in a certain way. I will note though, I know we can't really eliminate this from everywhere, but the hope would be to eliminate it in as many places as possible. The one area that I think this fits the most would be like a connection to Wi-Fi, where one of the preconditions could be to simply, actually, let me do one quick thing before I continue. I need to put myself on Do Not Disturb so I don't hear more of those sounds. Cool. Alrighty, so networking. One of the preconditions to using any networking application would be that you would need to, let's say you want to do a GET request, you need to be connected to the internet for that to work. And there's a part of me that wants to figure out ways to try to eliminate those surface area points. Does the code need to check? Should the code always need to support and handle an error in this case? Or could this thing be automatic where if you try to do a GET request and you're not connected, it tries to reconnect. And if it doesn't work, something happens. Just thoughts. Yeah, surface area requires some sort of handling either locally or at a higher scope. So yeah, whatever we can do to reduce our error surface area. Like I want errors that are meaningful and handleable. I do not want errors that just end up, we can have these, but I would prefer errors if they are if they're an error that's due to the API design. I think we should change the API in order to prevent those errors from happening. So that's pretty much what this particular area talks about. All right, so now we have SPI bit order policy. HAL SPI, the interface, does not have a configuration for bit order. I never considered it, mostly because I've almost always seen the bit order for SPI be MSB. And I think I was looking at some Linux HAL APIs as well as some other HAL abstractions out there. And I noticed that they had a LSB first flag. I was like, oh, that's interesting. I wonder how many devices actually have LSB first. Because if like half of the devices that we find out in the wild use LSB first, then this is kind of critical that we include it. If more devices do that, then maybe I need to kind of consider LSB first as kind of like the default. But no, actually what really happens here is I considered it, but then I did a little research. One, I asked ChatGPT, and then I also just Googled around a little bit to find things that fit this. And it seems very predominant that SPI is MSB first, and it's rare to find devices that are LSB first. The issue up here talks about it more, but basically I was only able to find a single device that had LSB first, and the other devices that were similar were devices with a single input register or shift register. And it just so happens that shift register, it's hooked up in a way that is LSB first. And when I looked into the LPC40 just to see if it supports it, just to see, okay, well, if I wanted to support it on just that platform, what would I need to do? I assume there's a bit I need to set. It doesn't support it. It just purely has no way to support LSB first. So now this makes me think, okay, one of my favorite chips couldn't even support this mode. What do I do in that situation if we were to actually support this configuration? Well, there'd be a lot of devices that never use that particular feature. And there'll also be a lot of devices that simply wouldn't be capable of using that feature. So if you ever set that flag from true or from false to true from LSB first or whatever you're going to call it, let's say we call it MSB first and that's true. If you ever set that's false, the expectation for configuration, if it can't meet the expectations of the configuration, is to throw an exception, which just seems kind of lame. I don't like it. Whereas we can sidestep needing to throw an exception by just simply saying, hey, if you need LSB first, handle it yourself. Basically, you're going to reverse your bits in your whatever bytes you're sending back and forth, in order to reorder them if that needs to be done as well. May not need to be done, but depends on what you're doing. But you basically have to manage reordering from MSB first to LSB first to make your driver work. And if you think, well, that's kind of slow, I'm like, yeah, cool, but also that's a bad decision choice that chip made. And because it's so rare, not really a big deal. But if there ever is, for some reason in the real world, a reason to have an LSB SPI, I would just say make another interface. Because it's going to be one of those things where, you could wrap your SPI driver and something that reverses your bits, provided that byte order doesn't also change. And if it does, then that becomes another can of worms. Let's assume that it doesn't. If that ends up happening, actually no, because if you changed your LSB order, it doesn't change your byte order. So yeah, no. So you can just have a wrapper that does that for you for every single byte you want to transmit. And potentially that could be fast enough. Who knows? But yeah, if you need one, we just make our own little interface for that. But I think it's not going to be necessary. On to the next one. So refactor ARM interrupts API. So basically, I moved all of the Cortex-M interrupt APIs from being within the interrupt class and just getting rid of the class and exposing all the internal static functions. And all of the normal member functions were just transformed into normal APIs. So basically, we have Cortex interrupt initialized. Now we just have initialized interrupts, and then you give it the last enumeration value in your IRQ number list. If you don't know what that is, we'll actually talk about this a little bit more when we go into the guidelines for ARM Cortex-M. Bring up. Also note that I was able to get rid of this value function. Value is a constexpr function that converts an enumeration into its numeric value. I was able to I added in all of these extra helper functions so that the enumerations here could be immediately transformed into their basically you could pass in enumeration class types directly into these functions without having to worry about anything. Same thing with enable interrupt and disable interrupt. They also have variants that support not having to use HAL value. And I think in a lot of other places I will try to do the same. I want to have a generic enumeration concept. So if you have some sort of enumeration, you don't have to, you can have APIs that take enumeration directly. And yeah, also on top of this too, I've also added in a couple of handlers. So one of the things I find really annoying, and I started seeing this pattern come out in all my other demos, or a few demos here and there, is whenever I was dealing with hard faults, what I would do is I would initialize the interrupt vector table, and I would I'd set up the hard fault handler. It would just be a while loop. It wouldn't do anything special. All it would do is that whenever I ended up there, I could check to see what function I'm in, and if I'm in the hard fault function, then I know that I hit a hard fault. And then there's all these other faults that could happen. And I was like, okay, well, this is actually kind of useful. If I just default set these up for your interrupt vector table, which these are very small functions, so I don't think it's going to be too bad, you can automatically know what function you're in if you're in a debugger. So this is just a way to make debugging a little easier. These are default added into the interrupt vector table by normally, and you can replace these with your own if you like. Yeah, so I decided to rename hardware map type to resource list type, or just resource list. Probably just keep it just resource list, honestly. Basically, it fits better for what applications need, which are hardware resources, but can also be other things such as blocks of memory for streaming audio, like the example I had before when I was doing the MP3 player, a frame buffer for display, a mutex to lock objects. Like maybe you want to pass the mutex versus having the implementations or wrapping your implementations for certain hardware with stuff that can handle the threading or mutex stuff. Maybe you could just pass it in, or maybe the application requires a mutex that's not bound to a specific bit of hardware. Who knows? But I think calling them resources makes more sense than calling them hardware maps, because what does it mean to be a hardware map if you have memory or if you have a mutex or other objects? I don't know if it really makes sense. So, but yeah, renaming hasn't happened yet. I'll probably do it by an automated script at some point. All right, so libhal platform has been renamed to libhal ARM MCU family. So this is a template that you can use in order to create ARM MCU microcontroller family libraries. We'll take a look in a sec, but basically these headers include a DMA header, a pin configuration header, a power header, an interrupt, constants, and clock header. And I should have actually reordered this after I talked about the bring up, but actually I'll go back to this after I talk about the bring up. The platform is designed entirely around ARM, and other platforms will get their own templates. So in the future, if we have some sort of RISC-V MCU family, or we support RISC-V and that kind of stuff in their MCUs, we'd probably make a platform template that is similar to the ARM MCU one, but tailored for RISC-V. I have a feeling that a lot of the stuff that's going to be in the RISC-V side is going to be very similar to what's in the ARM MCU side. But I don't want to make the assumption, and it's a lot easier to just write this tailored to ARM than to try to make it very generic, because I was also realizing that the template for platform was pretty bare bones because I didn't want to be too opinionated. And by doing so, it's added more work for other people and allowed for more variation beyond what I would have liked. So we made this. Oh, and here we go. Here's the bring up guide. So let's go into the bring up guide. So for the bring up guide, we have to bring up ARM Cortex-M series microcontroller for libhal. There are several critical sections you need to do. So there are the Conan profiles, the linker scripts, the continuous integration, deployment, platform constants, and core APIs. And some of the other things that you need to implement, which will make it easier for developers to actually build out your libraries, would be power control, pin multiplexing or pin configuration. Sorry, I was yawning. Clock tree, and finally, direct memory access, DMA. And not all devices are going to have DMA. Not all devices are going to have a very sophisticated clock tree. I assume they'd have a basic one, though. I assume almost all devices have multiplexing, pin configuration. But I can imagine that there's a system that doesn't have that. And power control may have very minimal power control to the point where it's just simply all internal devices are just powered on completely. And, maybe you could put the whole thing into deep sleep. Who knows? But I can imagine a device implemented in such a way. So yeah, so we go over the get starting. You have what the Conan profiles are. I try to explain these here and all the different parts that are in here as well. I'm not going to go over this entire document. You guys can go over it yourself if you're interested. I have a couple examples from STM and LPC40. Go over the directory structure for profiles. Go over how linker scripts work. Well, specifically, I bring some links to where you can learn more about linker scripts, and then you can follow the rest of the tutorial to go into the rest of the stuff here. Here are some links to some linker scripts. This kind of defines how linker scripts are kind of set up, because if you notice, for these, we have STM. Let me zoom in a little bit. We have STM32F10XX4. That last digit here, that last character, is basically an indication of how much ROM is available, or how much ROM is available, because the RAM is actually fixed. So we use that to figure things out. The other two numbers here are not important for figuring out which memory layout to use. They are important for the chip size and things like that, and what the chip may support, but it's not important for the linker script. So these are X'd out, and then there's like a script that will, or part of the Conan file script, that will transform those letters into X's in order to map to the appropriate linker script. This little part here talks about handling multiple flash and RAM configurations. We don't currently support that. And then it kind of goes over some of the stuff here about how to set the linker and all that. You can see the little masking stuff happening here. Replace unneeded characters with an X to denote a generic script, and use it. Again, so continuous integrations here. All the stuff that you may need is all here. At the bottom, we have a section that goes over implementing the core APIs, which is just going to link to all of the other things for supporting DMA, pin muxing, pin configuration, and etc. And then also those interrupt APIs take an enumeration class IRQ, an enumeration class. The enumeration class has to be a standard int16. That is the maximum that a ARM Cortex device could ever support. That goes for all of them. I would really be upset if at some point they support some number that's not a power of like 2 to the power 16 or 2 to the power 15, because then this whole thing kind of gets a little janky, although it shouldn't be too bad. And then one thing to also add in is that whenever you have your IRQ numbers, these are numbers that hook up to the CPU. These are ways that the CPU is configured and mapped such that when a signal from a piece of hardware or some hardware hits the CPU, it tells the CPU to stop what it's doing, act as if there's a function call at that point in the code, jump to to the handler for that particular interrupt, do its thing, and then when it returns back, it returns back to your bit of code. This max here is the total. It basically, once you put it at the end of this enumeration, it gets the maximum number. It gets 1 plus the last number that it saw. And when you do initialize, you need to provide it a compile time number for the maximum number of interrupts you need that the system can support. Initialize interrupt will allocate that memory statically and then bind the interrupt table to that bit of memory, and also sets it up and all that stuff. So yeah, so that's pretty much the bring up guide. If you see any problems or mistakes with it, if you have time, if you can make a PR, that'd be great. If you don't, make an issue. If you don't, just ping me on. If you don't have time for that either, just ping me on the Discord. But I prefer, at the very least, an issue. But if you can fix it, that'd be even better. Okay. And I'm also going to click on this so we can go over to the ARMMCU family file, and we can go over to include, and then we can look at clock. Clock is interesting because it basically just doesn't have anything here. You basically have to model the structure relative to the number of knobs and switches you can configure for your particular system. For LPC, the number of configurations is very minimal. And then when you look at STM stuff, it gets so complicated that even if I wasn't trying to build something generic like this or build something that could just do it all in a single function, it's hard to keep track of just looking at it when you're using it yourself. So it's honestly just an absolute pain in the butt to do clock tree stuff for STM devices that I've seen. There's a maximize all clocks API, which tries its best to maximize as many clocks as possible. There are some clocks that won't be able to be maxed out completely. One example would be for the STM32F1, its USB clock. The source to it can either be 48 megahertz or 96 megahertz. And I believe, actually, I think I'm wrong about that. Actually. I forget exactly what those numbers are. Actually, what is 48 times 1.5? I remember what the clock divider was in the chip. Let's see. 48 times 1.5, 72. Okay, actually, that would work. But in some cases, certain clocks, in order for them to be valid, need to not be their maximum value. So we don't set the maximum values. So whatever is the maximum that seems reasonable for that system. And then maybe a few other things like, are we using an external oscillator? This is a useful API for, and the idea is that this would actually hit the real hardware to get this information. And in general, you don't usually need to inspect this information. The code could, but I don't know if it's that useful. It's specifically useful for drivers that the datasheet tells you need to ensure that they're using an external oscillator, otherwise they are unstable. An example of this would be CAN for LPC40. It says in the datasheet very clearly, if you want to use clock speeds above 100 kilohertz, you need to use the external oscillator and also use the internal, and also use the PLL. PLLs are used to multiply up clocks like that. You need to use those in combination in order to create a stable square wave that can be used to clock and control the CAN peripheral. So if this thing comes back false when you try to use it above 100 kilohertz, it will throw an exception. And yeah, this is a function that allows you to apply your clocks. And I'm not going to take too much longer here. Constants are used for powering up peripherals, and they can also be used for a whole variety of other things as well. DMA is basically a single API that explains how to set up a DMA transfer. In general, all you really need to know when it comes to setting up DMA is just simply, actually, do I have an example here? Oh, I do. Nice. All right, so here's my DMA type. We have the source where we're getting our data, where we're putting our data, how long the data is, the type of transfer, which could either be memory to memory, memory to peripheral, peripheral to memory, peripheral to peripheral. The source transfer width, the source peripheral, and the source, if we're going to increment the address every time we do a transaction, and the same thing for the destination. As a quick little example, if I was going to stream data to the DAC, I actually use basically the same actually not the same exact setup, but something similar. The source would be my array of PCM data, my array of audio data. Then here we would have the destination be the single 16-bit register, or it's 32-bit register, but we're going to hit the 16 bits of it. That would be my destination. The length would be whatever the length is of the source, although if the source is really long and longer than what the DMA can handle. The design choice that I have for this is that the DMA handler should basically iterate through the blocks until the entire thing's finished. Just so that the logic can be centralized in one spot and not have to be redistributed everywhere else. If we had the length, if we had to ensure that the length was less than the length of the whole transaction was less than the maximum amount the DMA can handle. For example, for LPC, I think it was maybe it's this, I forget, or maybe this was what was this for? Maybe this was for LPC. I don't remember off the top of my head, but let's say it's like 4K. Cool. That means every bit of code that calls the setup DMA code will then need to have some conditional to check, hey, are we bigger than that? If so, do this looping code. Otherwise, just call it immediately. Or just put in a loop and the loop would finish afterwards. If we can put the loop directly in here, this will be the only place where that logic's required, and every other place can just ignore that. And again, this has nothing to do with preconditions, but like I just love APIs where you don't have to think much. You just give them the stuff and they will handle making everything else work. And you're going to see that example in other aspects in this code. So the transfer type would be memory to peripheral because we're sending data from RAM to the peripheral's register. The transfer width is going to be, that depends. When I was doing 16-bit, the transfer width would be 16. The source peripheral would be, in this case, memory, because we don't need to actually talk to our actual peripheral, so just put memory here. Source increment, this would be true. We want to increment, after we transfer the 116 bits, we want to move to the next 16 bits to transfer that as well. Destination would be 16 bits. The peripheral, destination peripheral would be the DAC, whatever code that needs for the DAC. And then finally, we have the destination increment. This would be set to false, because we want to stay on the same register. We want to basically just keep hitting that same register over and over again. And that's how that DMA stuff would work. And then I think, there's a callback. So once the entire amount is transferred, then callback can be called. Now, I'm seeing this initialized DMA, and I'm thinking to myself, because I have it on first call, enables DMA, once enabled, additional calls to the function do nothing. I might actually just remove this and just say that the first call to this API, I should just do that. The first call to this API initializes DMA. That way, the user doesn't have to worry about calling this first. Why deal with that when we just don't have to? So I'm actually, can I do this real quick? Let's see. Can I just, boop, and then can I make a issue, reference a new issue? Yeah. Remove, how does that even look? Oh, cool. Okay. Remove this API, consolidate into setup DMA transfer. Yeah. Sounds good. Yep. Let's put a little that in there. I'll assign that to myself. And nope. Yes. And submit. Cool. All right. So I'm gonna do that later. So that's that. Let's go back here. And what else do we got here to talk about? Interrupt is, I already talked about interrupts enough. Pin. There are a couple APIs. There is, no, there's only one API. What were the other ones for the, oh, no, I'm thinking about something else. I'm thinking about power. Yeah, pin configuration. So there might be a whole bunch of configurations for the different pins, and I would kind of consolidate all of them together into one big set. And if a particular pin actually cannot support a particular configuration, I think it makes sense to throw an exception at that point. It's the same thing as configuring anything else. If you try to if you configure it with something that is impossible for the platform, it can throw an exception. If it can determine that it can be ignored without problem, like for example, if you have a configuration for setting something to an analog output, but you're also configuring it as some sort of like SPI signal, then you could throw an exception for a bad input. But you could also, I don't know. It's one of those things where it really depends on the context, but I would assume I can't make any judgments yet. I don't know the full implications of what could go wrong. But yeah, that's configure pin. And then finally, we have power. This is the one with the 3 APIs. So we have power on, is on, and power off. I don't expect power on to be used very often. Probably use it a lot in like unit tests if you're writing unit tests for your platform, and you have substituted out your registers for like power control. But I could see some code potentially wanting to use is on in certain cases. You can also power off stuff. That's useful in a destructor. And then also power on, which is useful to, you need to do that in order to power on any of your peripherals. The assumption here, yeah, actually, I was else to say here. So yeah, that's all the different APIs here. I think this thing just has a, oh, right. There is an initialize interrupts function here. And this is just a way to consolidate all of the, like, basically that call we had before, which was, yes, this one here. Initialize interrupts IRQ max, just to make sure that the calling code can never mess that up. You just have a function that does that for you. And that's pretty much it for the ARM MCU family. All the other stuff in there is, if you've done this stuff before or looked at it at all, you've probably seen it. If you haven't, you can look at the bring up guide, and it'll tell you all the stuff you need. All right, so fundamentals doc has been added, although there is a missing board library section. Basically, I've added in a whole bunch of other sections. I kind of revamped some stuff here. I brought interfaces back up to the top. I realized I'd put it at the bottom, which is kind of confusing because it's described a lot in the beginning section. So starts off with interfaces and explains how these are the basic building blocks of libhal and enable our flexibility and portability. Ooh, I have flexible twice here. I should remove that. But yeah, here's like an input pin. I described some things there. This also describes why there's a private virtual function and why we have public APIs for stuff. We go over the different driver types, which are peripheral drivers, device drivers, and soft drivers. Go over the different types of packages. So I don't think I had compiler package in there before. I cleaned up the specification for the processor library. I go into detail about the platform library and the kinds of peripherals that could exist. And then, oh, snap, actually. This is wrong. Okay, so there's a problem here. So these should actually be tabbed. So these should actually be like subcategories. So here's some peripherals that can interact with the world, like output pin, input pin, I2C, serial, and so on and so forth. Here we have here are some peripheral drivers that can interrupt the CPU when a programmable event happens, like timers, interrupt pins, and watchdog. I swear I looked at this, but I think I caught this one. Where is it? There's another set of, wait a minute. I could have sworn this was the one that I fixed. Oh, that's interesting. I actually did fix this, but I don't know if the stuff got rolled out. Whatever. Actually, let me zoom out a little bit. Nope, same issue. Weird. I could have sworn I literally checked this an hour ago, but whatever. And then last we have some peripheral drivers that perform work for the CPU without the CPU needing to do that work. So, for example, holding real time is not holding time and holding real time are not things that the CPU could spend time doing. You could technically have an interrupt that occurs every millisecond and ticks up each time. It's not the worst thing ever, but if you could have a clock that did that for you, that'd be great. Now, if you need that functionality of interrupting every millisecond for something else, like an RTOS or an operating system or some other thing that you need to do, that's fine. But if you just want to hold time and hold time really well, real-time clocks are great for that. If you need to generate a CRC, there are devices with hardware accelerators for that. And there's also devices with graphics hardware accelerators in them as well. So these are things that, like, peripherals that don't interact with the world. Technically this one does, but actually depends. If this is a graphics accelerator onto a frame buffer, then no, it doesn't interact with the world. But they do work for the CPU. So then we have our device libraries and soft libraries, utility libraries, third-party libraries are explained here as well. I explained a little bit more about process libraries. I got rid of the application libraries because I want to have something a little more concrete to explain that. I don't really have anything for process libraries either, but I know this is a concept that we're going to make our way to at some point. And I think everything else in here is pretty much the same. So yeah, so I recommend people take a little look through the fundamentals of libhal guide again, just so you can make sure you're up on things. Okay. All right, now for the fun part, in my opinion. The low power strategy. So number one, I believe libhal should support low power operations. I've deferred thinking about this for a while because I wanted to make sure that other parts of libhal were figured out before we figured out low power. To me, I honestly looked at low power and thought, if we need to make a breaking change to support low power, I'll make a breaking change to support low power. And I'm hoping that it doesn't cause too many issues. And I was also kind of just waiting for my brain to think about it more on occasion and maybe come up with an idea. Thanks to Aaron for our conversations, because he showed an interface that had some power state stuff, and I told him, yeah, you shouldn't keep the power state stuff in there because I haven't decided on how I want to do power. But as I looked at his interface, I noticed certain types of patterns in it that I didn't really like. This is nothing on Aaron. There's more just it made me think about what power states can do and what viral behaviors they can create. Go into that in a little sec. But yeah, application developers will want to put their systems into low power mode. So for example, let's say you have an MP3 player, like the one I kind of made last week or 2 weeks ago. Let's say we have a power button. I assume if I press the power button, or if I have a power button for something and I have a screen that turns off the screen, the MCU gets put into low power state, and any sensors like that, let's say I have like accelerometers to detect things like footsteps or whatever, and a codec, they all should be put into low power mode. But do understand that low power mode is not full system shutdown. In full system shutdown, you completely turn off, and all state is lost. Besides maybe any state that you saved into non-volatile memory. When you boot back up, you have to start up from scratch. This is putting yourself into different versions of low power or suspended states. Although there is one version that is just shut down, but I have an explanation for how that works. All this is subject to change. So if anything that I say seems wrong, or even like just simply you have an idea about how to do something, or I realize there's a problem with my ideas, these will probably change. This is my first go at this. First go at this for libhal, I would say. And actually, one last thing I'll say is I have done low power work back when I worked on the watch for Google. So I'm taking what I've learned from working with like stuff at that level when I had to do it for a previous iteration of the watch, and trying to apply what I learned from that and try to ensure that I don't have to deal with the annoyances that happened before. So principles, there are 3. Number 1, power control APIs are outside of interfaces but abide by a libhal concept. Number 2, and I'll go into all these in detail in the next set of slides, there should be no API for bringing the device out of low power states. Number 3, power control APIs must be consistent for the power category states and should have the signature of void and void, but their names will be a little different. So there can be an idle function, which puts the system into a low power state. The idea with this is that if you put your device into idle, it's not as active anymore. It'll draw less current, maybe not the lowest amount of current, but it'll draw less current. But if you try to interact with it, it'll come right back into active mode. This is used. The idea here would be that, because you may ask yourself, well, why wouldn't we always just keep it in idle? Which you could. You could have it automatically always idle after you do any operation. And there's no reason why a constructor for such a driver couldn't supply you with that flag to tell you, hey, do you want to set this as automatically idle? What I've noticed in the past is that when you do automatic idle, your response time gets longer. Typically what happens is you may need to pull a register to get the thing, or let me think about this for a sec. For the device that I used back in the day, what was the problem that we had there? I think there was like a call and response where you had to access a specific register and see if it's available. And the act of simply talking over the bus to the device was enough. I think it was I2C or maybe it was SPI. But basically, we talked over our port, and that wakes up the device when it sees that it's been chip selected. And I think it was SPI. And then from there, it can then come back up and then do its work. So I think the rule was like, oh, read this register, and if it turns to a 1, then you're good to go. And normally it would turn to a 1 the first time you read it. Deep sleep. So deep sleep, in my opinion, and we can change the names for these things later on, a device that is put into a suspended sleep state, or some sort of suspended sleep state. The system retains memory in its state, but is not active. And there needs to be some work to bring it out of deep sleep and make it workable again. The idea here is that it takes even longer for these things to happen. So deep sleep, if you're going to use it, you have to tune your design, your application with that in mind. Shut down completely turns off the device, and it draws little to no power is the idea. But in any configuration, the state that you had before is completely destroyed. To bring this back up, the state of the system must be remembered by the driver in order to reestablish a state that the application relies on. So for example, let's say you have a display and you powered it off. Or let's say before you powered it off, you knew that you configured the display such that the format for the encoding was going to be 8-bit color. We did some sort of like weird mapping internally. We do all these different configurations for what the user specified at construction or at some configuration point. If we only had idle and deep sleep, you would not need to record the information to make shutdown work. But if you want shutdown to work, you would need to reestablish those such that the other operations can work. And I'll talk about why this is kind of an important thing in a little bit. First, let's talk about the non-interface API. So the power strategy will not be involved in any API, and actually I should have said interface is a better way to say that, not any API, but any interface. The power control capabilities between devices varies wildly. You can have one IMU that has power states and another IMU that has none. I mean, shoot, I've seen IMUs that output analog values. I don't even know if those devices are so simple in their design and how you set them up that like there actually isn't even like a way to put them into low power mode besides killing the power completely from them. Now, luckily they don't have any state either, so it doesn't really matter if you powered it off and powered it back on. You'll just maybe have to wait a little bit for the setup and hold time from reset till the actual like analog values have stabilized. That'd be pretty much about it. But because of all these wild differences, adding these to your interface would increase. Adding all these different power states. Let's say there's one for idle, deep sleep, and shutdown, would increase the vtable by n, where n is the number of APIs we decided to add for power. And the other thing that kind of sucks is that if you have a device that doesn't ever use it, then you have vtable entries that are basically taking up space that do nothing. And what I would want to probably do by default is that if you don't support a particular power state, when you call it, it just does nothing. If you try to shut down and it doesn't do anything, that's fine. To me, like even though it ought to lower the power consumption, I guess the way to think about this is that any one of these power APIs shouldn't increase power consumption, but it can either be equal to what it was before or less. And it really becomes opportunistic. So you can call these APIs if they're available to you and they work for your use case. But if we had it inside the vtable, you would opportunistically call them, but you may not get what you expect, really. And it would also, if you ever needed to, well, yeah, I don't think I need to go into that any further, but yeah, that's pretty much the idea. But the other idea here is that a concept could check if a class function exists for idle. So for example, you could write generic code such as how idle, give it a whole bunch of your drivers, and then it will figure out how to call all of your idle functions. It'll say, oh, parameter pack, here's like all the different types that were passed into the function. Here's how we call all the APIs. The concept can be called something like idleable or shutdownable or like deep sleepable, something like that. So that's pretty much the idea of why we don't have inside the API. It's just, or inside the interfaces, because it doesn't really make any sense. And I think we can get what we want without needing that. Oh, and actually, one last thing is if you have I didn't add this in as a bullet, but I think it's also kind of interesting too. What happens when you use make functions on such a thing? So, for example, if you have a singular, I call it like object splicing or interface splicing, where you have a certain object that has the ability to be multiple other interfaces if you ask for those parts. So let's think about the smart motor, or actually think of an IMU. The IMU may have accelerometer, compass, and gyroscope capabilities. We could call shutdown, sleep, and other things on all these other ones. Kind of a problem here. Well, I guess all of them could know the state of the original IMU and then change as accordingly, and then they all map to the same IMU, so it shouldn't be that big of an issue. So maybe that's not a problem. But I think it's a bit confusing. Whereas if you have the full concrete objects you're controlling the power of, I feel like it's a little easier to reason about. All right, so this might have been really confusing. Well, how do you handle your APIs? If you're going to power down your stuff, how do you power back up? And the answer is call any API on it that needs power. Basically, the idea is that make it automatic. If you have an IMU and you put it into low power mode, and then later on want to read it, the IMU should notice, hey, my power state was deep sleep. I need to bring the device out of deep sleep, wait my setup and hold time, and then read out the value from it. That way, users who use your APIs basically never have to think about whether or not they're in any state. They just simply use it as they normally would use it, and it will do all the work automatically. And one of the things that I did not want to happen is this pattern here. If driver is powered down, power back up, then call the API that you wanted, effectively, so I could see someone making a macro or a helper function or something that does these checks for you. And that brings us right back to what I disliked about, in a way, I found that I just really dislike, this is already a precondition really. This is a precondition check. Hey, is a precondition that this thing's powered on? No? Check it, okay? It's not powered on. Cool, call the thing that I need. This will be added throughout the entire code everywhere automatically for you. That sucks. Especially because I bet that API might also need to do that check internally as well. So in order to eliminate all of these checks, effectively what we want to do by making this automatic, we keep the branches and power state checks to the lowest driver level, and no other API must be concerned with power state. So all other code operates normally, and only the driver that actually understands how to interact with the device will ever have to think, do I need to do some setup time, wait a little bit, turn this thing back on, and then execute? Now, will that affect your performance depending on how you use this? Of course it will. That's actually something you need to keep in mind. If you're going to power something down, you need to keep in mind how long it takes for it to boot back up. So if having your display always be on and active is important, then don't ever shut it down. You'll burn energy, or maybe put it into idle mode, something like that. And here's a bit of like an example of how this could happen. So imagine we have a display, an MCU, and an MP3 codec. And all three of these things have power states that can be controlled. And assume this connects up to some buttons. This is our little MP3 player. So everything's active, an off button is pressed. The display goes into complete power off mode. The MCU goes into sleep mode, waiting for any other interrupts from a button press to wake it back up. And the MP3 decoder gets put into sleep mode. A deep sleep or something along those lines. A button is pressed. So let's assume that when the button is pressed, the MCU can read out what button that is. Let's say it's like the home button. And what it does is, I'm going to change the state to the home button. And then what I'm going to do is I'm going to update the screen. In order to do this, in order to get it out of power mode, there's nothing that needs to be done. Simply, the MCU just wakes up, updates the screen to the appropriate new screen display frame buffer. Basically, it updates the screen. The act of trying to update the screen will do the work of the driver going, hey, we need to re-establish, we need reinitialize the screen, and then update the screen so that it shows this new image. And then after that, some idle timer hits, and the system goes back into idle. It's no longer powered off, so display still on. But the display can be put into a low power mode. The MCU can be put into low power mode, so could the MP3 codec. Then, through a combination of buttons or whatever, the play command's been pressed, and now with this MP3 player, we can imagine that it's trying to like show a progress bar or maybe some animations in the background. So the screen's being updated, the MP3 is getting fed, receiving MP3 data from the MCU, and then when the pause button is pressed, we go into low power mode because we don't need to do anything. We could stop, we don't have to update the screen unless we're doing more animations. And we can stop the MP3 decoder because it's no longer doing any work. And that's kind of the idea, is that all this stuff should just flow naturally. And if you wanted to put your system into a low power state, you would either do that at the tail end of your super loop, or you would put that at the tail end or like inside your idle task for your operating system. So anytime it drops in there, maybe you could either always try to go into idle immediately, or you could attempt to, and that depends on your architecture if it can support that. Or you can wait a certain amount of time before you decide to put everything to low power, whatever your application needs. And how you actually use this in the code, basically in your initialize function, you could, or wherever you're constructing your resource list, the resource list could just simply have like an inter idle and inter lowest power state. So in this case, when you have inter lowest power, you could just have display shutdown, decoder idle, and then put the device into deep sleep. Whereas with inter idle, you idle the display, you idle the decoder, and then you idle your platform. And actually, there's like a power saving mode that ARM Cortex devices just have. There's an instruction called wait for interrupt, and you could basically just call that function that puts the system into effectively into a low power state, waiting for interrupt to occur before it wakes back up. And that's pretty much the idea of how you'd use it. So to me, it seems relatively simple. You just give a callback for what's needed to power the thing down, and then any calls that end up powering back up, power it up. The thing I also like about this, kind of looking back at this example, is that if you are spending most of your time in your idle task, and your idle task just puts it to sleep and then waits until something happens. Oh, side note, if you ever use like the wait for interrupt, you're going to want to idle everything else first before you idle your platform. Otherwise, you won't be able to get to the other callbacks here because you'll jump out. I could see some weird behavior happening if you were to idle the platform first and then idle your other things. But yeah, so let's say you had a whole bunch of different systems in your system, and not all of them need to be used all at once. Well, if your idle function idles all of them, then the only things that you ever bring out of power, any sort of power saving state, would be the things that you actively are using. And to me, I feel like that's a very simple and elegant way to ensure that you're using the least amount of power necessary to keep the system running. And that's pretty much it.